use Vertica examples in my presentation because they're the only customers who want to talk to me these days. So my presentation is all about how to get your Python work, your machine learning work into production faster, because we all know that it doesn't start bringing money back in. It's just a cost center until you can get it into production and earning money for your company. And then you can do some pretty amazing things. So getting it into production is the big hurdle. Now, my presentation has absolutely nothing to do with space, but I put stars all over it because I'm kind of a space geek, and I'll figure out some way to incorporate it into my presentation. So let's start with Philips. Philips this is actually one of their slides. And it is a good example of somebody who needs to get machine learning into production and who has actually been in production for quite a while now. In fact, they predate some of the technologies that are out there, and yet they have tweaked their architecture as they go along to take advantage of cutting edge capabilities. So they have 1 foot in the past and 1 foot in the future, and they're a pretty cool example. They're also a pretty generic example. It's like, this is a good kind of a general idea of how this usually works in production in a company. And it starts with all the components of the devices that they create: MRI machines, CAT scanners, ventilators, really important machines that we absolutely don't want broken. All of the components of them have phone home capabilities. So they're sending information back constantly about how they're doing, what their temperature is, what, how many times they've been used, what the, all this kind of information. It's IoT kind of stream of data, which is coming back, and they have been collecting this information for years. Now they take that information and they combine it with some contextual information, like, when was this device purchased? When was it last maintained? What was replaced or fixed the last time it was maintained? What's the geographical location of this device? Is it in Minnesota where it's, and it's January and it's -20, or is it in Texas where it's 105 in August? It's like, what kind of things might affect this machine? And then they take their algorithms and, Python algorithms, some kind of good sophisticated machine learning algorithm, throw it against that massive data and refine the data and figure out, okay, this is the data that indicates something important. In particular, it's going to tell me the pattern for when a particular component in a particular device is about to break. So what they're doing is they're moving from, a hospital calls up and says, my thing is broken. And this MRI machine that everybody needs is down for like a week or two while they go look at it and troubleshoot it and try and figure out what the problem is, and maybe go back to the warehouse and get a part. Oh, that's the wrong part. Let me try again. To a model where they know that this particular part is about to break. So what do? They send somebody out there to fix it at 3 a.m. or something when the machine is not being used. So the machine is never down. It's never not available when someone needs it. And that's really powerful that's incredible value both for their customers, for Philips, and for, the general public who might like to have that machine available when you need it. So how are they doing that? So this is kind of a high-level look at their architecture, and I'm not looking at the edge here. There's lots of presentations on how to do IoT edge stuff. This is just particularly how to get your machine learning into production, especially if you're doing it in Python. So in this case, they are pulling all that data in, and they're putting it in a data lake. They're throwing their algorithms. They're not actually throwing their algorithms into the data lake. Oh, that's kind of a surprise. A lot of people expect the only place you can do data science is in the data lake with that raw data, or with some refined version of that raw data. But they're not doing that. They're refining the data and they're putting it into a distributed analytics database. And when they go in real time to try to detect whether or not something is wrong right now, after they've trained the algorithm in the database, they now use the model to predict and figure out this thing is about to break and schedule maintenance and take care of that. And they're also doing BI because, just because we're doing data science doesn't mean a business stopped having to do BI. They have to do both to run a business. But the main thing I'm looking at when I look at this is that they're doing it all in that distributed MPP analytical database. Why? Why are they doing that? Well, back in the day, we kind of had this concept that a data warehouse, an analytical database, couldn't really handle IoT data. It couldn't handle the multiple types of contextual data like geospatial shapefiles and things like that. It couldn't handle the massive volume of storing 5, 6, 7 years worth of information. It just wasn't, it wouldn't work. This was not possible in the past. Well, things have changed. So now databases are distributed, and the analytical database is now MPP. It's now capable of scaling just like Hadoop, where you add another computer and it gets bigger and it can handle all the scale that you have or that you need and in one place. And that's pretty cool. But it's a SQL database. Everything you can do in it, you do it in SQL, and that's fine for BI, but data science, you usually want to do it in Python or R. Well, this database has distributed R built in. It has Python capabilities built in. So I can take a Python algorithm and I can put it in this database and it will distribute it. And it will do the, it will apply the algorithm to slices of the data across the cluster. Well, that's weird. Is it because Vertica is this super cool, awesome, unique database? Well, I'd love to say that that's true. And certainly it is. We are super cool and awesome, but we are not alone. There are a lot of databases out there that can do that. So Google BigQuery ML is a good example. They have a machine learning capability with Google BigQuery. If you want to do Oracle Autonomous, has great R capabilities built in. This is something that is real and that is happening, and that a lot of companies that are trying to get past that hurdle and get their stuff into production, this is how they're doing it. So let's have a look at this. It's like, what do you need to make machine learning work, to get it into production? Well, you got to have speed, especially in an IoT kind of use case or any kind of use case. Let's say I'm doing real-time ad targeting on the web. If I click on something and I want an ad, I want to accept bids on that ad and then place that ad all before the website loads. I need that in microseconds. So I need some fast response. I need it to be easy to use. So something like SQL or Python, which is a high level of abstraction, that's something that I got to have. I got to be able to do a lot of stuff, a lot of different functionality. Machine learning has like hundreds of applications. So I got to be able to use it for whatever it is I need. I got to have the flexibility to put it where my production system needs to be. I mean, one company may need it on-prem, another one needs it on Amazon Cloud, another needs it on Google Cloud. It's like, you've got to be able to put it where it needs to go. You need to be able to handle a change. You need to be able to handle all the data sources that you got to pull in. You got to be able to handle crazy algorithms because the algorithms are constantly changing. It's like, and you've got to have an open architecture because there isn't just one thing that does this. This is almost always, I mean, that architecture didn't have one technology in it. It had a whole lot of technologies, and all of those technologies not only have to be good at whatever it is they're doing, they have to be good at connecting to all the other things that they're doing to make the whole thing work. So you can't just have one good component. You have to have all the components working well together. So what does Python have going for it? Well, it has a lot of functionality. It can do a lot of different things. It's flexible. It can go pretty much anywhere. It's fairly easy to use as programming languages go. It's got a high level of abstraction. And if you want an even higher level, you can go use a Jupyter notebook or something like that. Python is really easy. as programming languages go. So, and there's a strong community. There's a lot of capabilities. There's Scikit and Pandas and all of these packages that are coming out. So this is cool. Python is awesome. Python can do everything you need it to do. It can do all the things machine learning wise. It can do all of these great use cases, but it has some problems. In particular, it has trouble with scaling, and not just scaling to have large data. I mean, it has global interpreter lock and CPU thread management and all these technical problems that cause that problem. But what it really comes down to is once you get past a certain scale, Python doesn't work well. And once you get past a certain number of concurrent users, it also doesn't work well because it doesn't like divide up resources well. So if I have 5 people in my data science team, that might work. But if I have 15, it doesn't work. If I have 100, forget it. that's not even in the realm of in the realm of possibility. So we all know that data science isn't like this thing that I do. It's like, oh, look, I did data science today. It's like, it doesn't work that way. First, you got to figure out, what's going on. You got to look in the data and do some, exploration and figure out, is this going to work? Is this going to answer the question? Then you got to prep the data so it's just right for answering that question. You got to train a model. Your model is terrible. You got to start over, get a different model, try again, evaluate this new model. And you're like, hey, this one looks like a good one. It's like, hey, now I've got it. And bam, you hit a wall. Now, this is what people keep coming up against over and over again. It's like trying to make that final jump into deployment is difficult. And I got to ask, why? Why is it hard? Well, there's several reasons. One is a person is subsampling. They're taking a small amount of the data and they're going off and working somewhere else because they're working in some kind of technology that really can't handle that scale. They can't move all of that data somewhere else. What do I do? It's like, well, I move this little bit of data. Well, but that's my production location. It's like, once this is great, how do I then get it back to where I started from? It's like you're running into some difficulties there, and you've got to have that speed of response. And a lot of times that can be difficult to get. So, well, I mean, the answer to how to improve my accuracy is pretty obvious. Use all the data, don't use a sample. Okay, well, that's easier said than done. I mean, we all know that that machine learning models do better with more data. I mean, that's why it's kind of taken over the world right now, is because all of a sudden we can process the amount of data, and that amount of data is available to us where it wasn't before. I mean, I studied artificial intelligence and machine learning and stuff like that, 20 years ago, 30 years ago, but it was largely theoretical because a lot of what we needed to do, we didn't have the processing power to do that unless you spent some ridiculous amount of money. And now you have that capability to get the full data set and get the maximum accuracy. And sometimes a single point of accuracy can make the difference in your business between being lucrative this quarter or being not lucrative this quarter, and making you look like a rock star or making you look like maybe you don't deserve your salary. So, here's the other problem. Data isn't all that big data. It's not easy to move. Well, what do? Bring the analytics to the data. Don't try to bring the data to the analytics. So here we go. I got that space thing in there. I knew I was going to get in there somewhere. Data has gravity. The bigger the data, the harder it is to do things somewhere else. The more you're sort of pulled towards that data, as opposed to trying to pull that data somewhere else, because the more data you have, the harder it is to get it moved to somewhere else. And the more it makes sense to leave it where it is and to bring other things to it instead of the other way around. So bring the model to the data, don't bring the data to the model. I might repeat that a few times because I think it's like a fundamental principle that you need to think about whenever you're trying to architect data science and machine learning and AI and all those things. It's like you not only get the parallelization capabilities in place, you not only get, you don't have to move your data, you don't get slowdowns, but you also get the security and the provenance and all the things that the governance, all the things that a mature technology is likely to bring. So if you've got all your data sitting in the database and that's your production system, it's like, why would you go do your data science somewhere else? Why would you go somewhere else to do it when that's where the key data that you need is sitting? It's like, it makes so much more sense to take it to where it needs to be. Now, the other thing is just that you need speed. A lot of use cases require sub-second response or a few seconds response, and that's just not what some of the other technologies are built for. Nobody built a data lake with the idea that I would look at 10 petabytes of data and respond to you in less than 2 seconds. It's like, that's just not what it's built for. Whereas analytical databases, that's exactly what they were built for. That is their goal in life, is to give you a fast response. So let me look at another example. So this is Uber. Now, this is actually Uber's architecture from about a year ago, because they've done a lot of work to it, and they it's almost one of their hobbies is tweaking their architecture. And the reason is they have over 100 petabytes of data that they're managing, and every little teeny tweak that they can do that ekes a little bit more efficiency out of that system is money in their pockets, or is satisfied customers, is, it makes a huge difference to their model, to their business model, in order to, it's worth it for them. So what are they doing? They're taking data into a data lake. They're using Spark to do some ETL. Now they're putting all their data in the data lake. And this is the cool thing that they're done for anything that they need a response time between 1 minute and 5 minutes. They've created something called Hootie that has an ACID transactional capability on the data lake itself. So they can put all this data in Parquet, which is a really efficient way to store your data long term, because it's hierarchical, it's compressed, it's really good. And they can do ACID transactions on that, and they can do some data exploration. They can do some experimentation, some machine learning on that if they want to directly, using Presto or Spark or Hive or something like that, even Jupyter Notebooks. Or if they need a response that's faster than a minute, that's within a few seconds, then they take the data that they're going to need those high-speed query responses on, the most recent data, the hot data, all the data that they really are doing queries on really quick. They put that into a distributed analytical database. They're using Vertica, like I said. My examples are my customers. But you could use something else. I mean, they had a data warehouse. It was Vertica. They went to a data lake. Now they have a combination. So their progression is pretty natural. This happens a lot. You see this over and over again. Now here is one of the things that is important, is they needed workload isolation. They needed to be able to do multiple things at once. And so they created multiple databases. And now they can query data in this database. And if it's like, just, my poor barons, they can't take anymore. So if it's overloaded with queries, you can move the queries to the other database. Now it's got duplicate data. Well, what about other data that they might not get queried quite as often, but every now and then it needs? Well, they made another database for that, and queries to that will never interfere with these others. So they're all isolated workloads, and they could do BI, and they can do data science, and they can use Python, and they can put Python directly in there. And one of the cool things that they're doing actually is geospatial analysis, because they found out it works better in the database, and they can get a quicker response for things like route optimization, so they can get a car to you in under 7 minutes, or get your food to you while it's still hot or whatever. So this kind of, that sort of thing they can do right there. And because at the time, Vertica actually had a Python interface, but it was kind of terrible. I mean, it was good, It was very performant, but it didn't have all the capabilities. And they build all their applications in Python. So they were like, well, I want to be able to use Python directly on this database. So they created something called Vertica Python and they open sourced it. So this is what happens a lot of times is capabilities that companies need, they build, they open source. Uber is, you know, one of those that does that sort of thing. Now, moving forward, they're actually looking at, oh man, I had to build all this code so I can decide where to put my data. And then I had to build this proxy and I can go here. And now they're actually moving to Google Cloud in the future. And they're looking at using subclusters so that they can spin up a full cluster for one isolated workload and another cluster for an isolated workload, another cluster for like an ephemeral workload, and spin it back down and spin it back up, and you know, that sort of thing, without having to build all that code themselves. So that's going to be more efficient for them, and they're working on it right now. So in the meantime, it's like, what did the database bring to the table? What was it? Why is Uber using a database? Why didn't they just do everything on the Day Lake? Why didn't they do it in some data science lab or something else? It's like, what do they get out of it? Well, a couple of things. First of all, there's no single point of failure in that database. There's no name node, there's no master node, there's nothing that's going to make, you know, one node go down and the whole thing dies. It's like, that doesn't happen. You get fast response because that's what databases are built for, is high speed response, a few seconds, sub-second, milliseconds, that kind of response. And concurrency, because databases are used to someone doing business intelligence dashboard and giving it to 1,000 people, and 1,000 people drilling down at the same time and sending SQL at this database all at once. And they have to be able to handle concurrent users. So it's built to handle concurrency. It's got all these cool features. It can handle the ML. It's got built-in machine learning algorithms. It can parallelize your R, your Python, or whatever. It can do moving windows, geospatial analysis, time series joins, fast data prep, all that kind of stuff. And it has an open architecture, which means it connects with Tableau and Looker and, you know, all those, you know, guys on the visualization side and that sort of visual BI side, and all the ETL guys and Kafka, and it can interact with Spark data frames or Python data frames, that kind of thing. So it gives you a lot of flexibility. So concurrency, I think I already talked about that. But this kind of is just like, what can you do? Well, you can prepare the data, you can explore the data. Here's that, you know, circular thing that you're trying to do. You can sample the data. You can join two disparate time series sets and then impute missing values. You can do the kind of things that you need to do, the data prep to get that data ready. Then you can train your algorithms, and you can use one of the built-in machine learning algorithms that are already in there, or you can build one in Python and you can put it in there and then it'll distribute it, which is cool. And then, well, or maybe I already trained it and I want to score it, I want to check it, I want to deploy it. Well, you can just save it as PMML or something like that, put it in, and then it'll score it. It'll compare it with other algorithms. It'll do the things you need to do. And then most importantly, it will deploy it, because a database is the same as in dev, in test, in production. It takes one line of SQL. Boom, you're in production. 10 minutes instead of 6 months. That's huge. That's the big thing that a lot of people run into. So we get the power and the flexibility of Python and the scalability of Vertica, and that crazy little symbol there is Vertica Pi, which is our new Jupyter Notebook capability, which is open source. You can go out there and get it. So you can use Jupyter Notebooks now if you want to. So what do you get? You put your Python or your R in there, it distributes it, it takes care of, it puts your algorithm up against slices of the data. So you get that parallelization without having to write any extra code. And that's huge. You also get fast data prep and things like that. That really makes a big difference. And TensorFlow, let's say neural nets. Neural nets are better off trained on GPU systems, but your production systems are almost always on CPUs or on the cloud, or which has usually CPUs. And that causes you some problems. It's like, how do I get my TensorFlow into production? Same way you get your Python into production. In this case, you put it in frozen graph instead of something else. So that kind of gives you the idea. Go check out Vertica Python, Vertica Py if you want to. Here's some things that people are saying, which is pretty neat. People say nice things about you. That's always good. Check out vertica.com/try. This is a free community edition, up to a terabyte, up to 3 nodes. Try it out. It's got all the machine learning capabilities in it. You can do everything with it that you can do with the larger version, except it's just on a small scale to give you an idea of how it works. Or if your data is only less than a terabyte, just use it. It's yours. And if you want training on it, Academy, the Vertica Academy is free on demand. Gives you certification, looks good on your resume, that kind of thing.